Okay, we will continue with what we are doing in the last class. In the last class we looked at some of the numerical integration schemes like Newton-Cotes rules with 1 point, 2 point, 3 point, 4 and 5 points. 1 point rule is called rectangle rule, Newton-Cotes rule with 1 point is called rectangle rule, Newton-Cotes rule with 2 point is nothing but trapezium rule, and Newton-Cotes rule with 3 points is Simpson's rule. So we looked at how to get the weights associated with these integration rules, and also we looked at dominant error term for each of these methods, what is the order of dominant error term, and also if the accuracy is not sufficient we can go for repeated use of these rules, like we also looked at repeated trapezium rule, repeated Simpson's rule, and finally what we have noted is Newton-Cotes rules with n points integrates a function of order n minus 1 accurately, or if we require to integrate a function of order n we require to use Newton-Cotes rules of order n plus 1. And then we looked at Gauss-Legendre rules, again 1 point, 2 point. For 2 point Gauss-Legendre rule we also looked in detail how to get the locations of the points and also corresponding weights. Basically what we did is if we require to find if we require to find n number of unknowns, we imposed conditions such a way that we get n number of equations, so that we can solve these n number of equations for n number of unknowns uniquely. So that is the approach we followed to get the locations and weights of the integration points. Gauss-Legendre rule is also called Gauss quadrature, and why it is called Gauss-Legendre rule, because the location of integration points turns out to be the roots of Legendre polynomial. And also we looked at, in the last class we looked at changing the limits of integration, because some of these integration schemes require to have limits between minus 1 to 1, upper limit of integral should be 1 and lower limit of integral should be minus 1. In that case whatever may be the limits of integration we can change to minus 1 to 1 using some kind of transformation. We also looked at that one, and so far whatever we have seen in yesterday's class it is only a one dimensional integration. In today's class we will continue and look at even 2 dimensional or how to evaluate multi-dimensional integrals or multi-integrals. So before doing that let us look at what is this Gauss-Laguerre rule. Okay, before going further let us look at what is this Gauss-Laguerre rule, and this helps us to numerically evaluate the kind of integral that is shown in the equation, that is integral 0 to infinity e power minus x fx dx, similar to Newton-Cotes rules or Gauss-Legendre rules that we have seen, what basically we need to do is we need to evaluate function at some points over the domain between 0 to infinity and multiply with corresponding weights, and the number of points that we need to use depends on our choice. And why this word Laguerre? Because here it turns out that these locations of integration points are roots of this polynomial, Laguerre polynomial, that is why it is called Gauss-Laguerre rule. And let us see how we can evaluate this integral 0 to infinity e power minus x sin x dx using 3-point Gauss-Laguerre integration. And similar to Gauss-Legendre integration, we have well documented in the literature the locations and corresponding weights of the points, and they are given in this table. So before we proceed in estimating this integral, let us look at the table. So depending on the number of points we require to use, we can select the corresponding locations of integration points and the corresponding weights from this table. So the problem statement, it is suggested to use 3 points. So we select the locations corresponding to n is equal to 3 and weights corresponding to n is equal to 3. So we need to evaluate function at each of these points, 3 points, and multiply with the corresponding weights and sum them up. So that is how we can estimate this integral, that is integral 0 to infinity e power x sin x dx. And before that, some of the important properties associated with the weights and locations in this Gauss-Laguerre rule are as follows: sum of all weights is equal to 1, and weight times integration point location, and if we sum up for all the points, it is going to be equal to 1. So the locations and the corresponding weights satisfy these two conditions. And now coming to evaluation or estimation of the integral 0 to infinity e power minus x sin x dx, the details of calculations are given here, and it turns out that simplification of this results in 0.496. We can also find exact solution for this particular problem, which is actually 0.5. So the estimate is in good agreement with the exact solution, and if we require to get more accurate result, we can increase the order of integration, that is we can go for 4 number of points. So now let us look at how to evaluate multiple integrals, that is an area integral like this, integral fx dx integrated fx dx dy integrated over the region R. Here it is shown in this figure. So we require to evaluate this function over this region, and this function varies over this region. That is why fxy is inside integral. If fxy is constant, then we can pull out of the integral, then integral dx dy over the region R is going to be the area of that region R. So now basically what we require to do, we need to find this integral. We require to decide how many number of integration points we want to use along x direction and y direction. So this integral fxy dx dy is approximated as function this fxy evaluated at certain number of points along x direction, y direction. Here it is going to be a Cartesian product of all the points and locations of the points and the corresponding weights. So, we can estimate this integral using this formula, and which will be illustrated here. So, let us take a rectangular area like the figure that is shown on the left hand side, and now if you recall trapezium rule, and we are actually basically using 2 points in trapezium rule. So, the 2 points along x direction and 2 points along y directions are shown in the figure on the right hand side. The points, the integration points are actually located at the corners of this rectangular area, and the distance between these integration points along x direction is h, distance between the integration point along integration points along y direction is k. So, we need to apply trapezium rule in both directions, and this integral fxy dx dy integral double integral between the limits x1 x2 y1 y2 is approximated as 1/4 hk. H is nothing but the distance between the points along x direction, k is nothing but distance between the points along y direction, and function evaluated at 4 points, that is function evaluated at x1 y1 x2 y2 x1 y2 x2 y1. If you recall trapezium rule, this is basically applying trapezium rule in both directions, and taking Cartesian product of that results in this equation. So, now let us apply this formula to estimate an integral like this, integral 1 to 3 1 to 2 fxy dx dy, where this function f xy is xy times 1 plus x using trapezium rule. So, we need to apply the formula that we have just seen, that is we need to first identify what is h, what is k. H is nothing but the distance between the upper limit lower limit along x direction, k is nothing but distance between upper limit lower limit along y direction. So, h is equal to 1 in this case, 2 minus 1 is 1 and 3 minus 1 is 2. So, h is equal to 1, k is equal to 2, and then apply the previous formula that we have just seen, that results in this equation. So, we need to substitute what is the function value evaluated at each of these points, f11, f21, f13, f23. So, doing all that substitution, we get this estimate 16, and the exact solution turns out to be 15.333, and since we used trapezium rule, the accuracy is little bit less, but if we adopt higher order rule like Simpson's rule, maybe we can reach the exact solution with more accuracy. So, now let us see how to apply Simpson's rule over rectangular area. So, basically we need to evaluate function along 3 points at 3 points along x direction, at 3 points along y direction, total taking Cartesian product of these 3 points along x direction, 3 points along y direction results in total 9 points which are shown there, and the distance between the points are also indicated. Distance between points are x2 minus x1 is h, y2 minus y1 is k. So, with that understanding, applying Simpson's rule along x direction y direction separately and taking Cartesian product of that results in this. So, area integral of f x y between the limits x1 x2 y1 y2 is given by 1 over 9 hk times function evaluated at x1 y3, 4 times function evaluated at x2 y3, function evaluated at x3 y3, 4 times function evaluated at x1 y2 plus 16 times function evaluated at x2 y2 plus 4 times function evaluated at x3 y2 plus function evaluated at x1 y1 plus 4 times function evaluated at x2 y1 plus function evaluated at x3 y1. So, we can apply this to estimate that the integral that we already estimated using trapezium rule. So, this is what we estimated, this is the integral that we estimated, where f x y is defined as x y times 1 plus x. So, now we need to apply Simpson's rule. So, first we require to identify what is h, what is k. H is nothing but half the difference between the limits, upper limit and lower limit along x direction. K is half the difference between upper limit, lower limit along y direction. So, those two results in h is equal to 1 over 2, k is equal to 1, and now applying the formula we get this equation, substituting the function values evaluated at each of the points that are in the equation, we get this one, and finally this becomes 15.333, which is actually the exact solution. So, when we evaluate this integral using Simpson's rule, we closely match, or we almost get the same value as the exact solution. So, this is about integration over rectangular area using Newton-Cotes rules. Again, Newton-Cotes rules require a function of order n requires n plus 1 number of points to get accurate or exact solution. So, we require to use n plus 1 number of points along x direction, n plus 1 number of points along y direction, or if the function along x direction is of order n and the function is of order m along y direction, then we require to use n plus 1 along x direction, m plus 1 along y direction to get an exact solution using any of these rules, that is trapezium rule or Simpson's rule for rectangular area. So, now let us look at how to evaluate integration over rectangular area using Gauss quadrature rules or Gauss-Legendre rules. So, first we need to identify the locations of integration points, they are indicated in the figure, the rectangular area, and then since function is in terms of x y, we require to express these integration points in terms of x y, or this is the relationship between the integration point location with respect to the local coordinate system, which is denoted there or which is indicated there in the figure, and this is the relation, this equation gives relation between the psi coordinate system and x coordinate system. So, psi 1 is given by x1 plus h minus 1 over root 3 times h, and psi 2 is x1 plus h minus 1 over root 3 times h, where h is half the dimension of the rectangular area along x axis, and the corresponding weights at these 2 points is equal to h, this is the coordinates of psi in terms of x. Similarly, we can express eta in terms of y. Eta 1 is equal to y1 plus k minus 1 over root 3 times k, and eta 2 is y1 plus k plus 1 over root 3 times k, and the corresponding coefficients or weight functions or weights are w1 w2 is equal to k, that is half the dimension of the rectangular area along y direction. So once we have these locations and the weights, what we require to do is we need to take Cartesian product of these and multiply with corresponding weights and sum them up, then we are going to get the approximate value of integral. So hence the formula becomes integral fx y over the rectangular region x1 to x2 y1 to y2 is approximated as weight along x direction times weight along y direction, that is h times k multiplied by function value evaluated at all the 4 points, sum of the function values evaluated at all the 4 points. So now let us apply this formula to evaluate this integral. Integral x cube y power 4, we need to integrate over this area 0 to 2 minus 1 to 0. First let us check what is the order of this integrand along x direction, it is 3. So 2n minus 1 is equal to 3, so it turns out n is equal to 2, and along y direction 2n minus 1 is equal to 4, so n is equal to 2.5, we need to round it up to 3. So to evaluate this integral accurately or exactly, we require to use 2 points along x direction and 3 points along y direction, but here in the problem statement it is suggested to use 2 points along both directions. So we can expect some kind of error when we evaluate this integral using this 2 point Gauss-Legendre rule in both directions. So first we require to identify what is h, what is k. H is nothing but half the dimension along x direction, that is 2 minus 0 divided by 2, which is 1. Similarly y is half the dimension along y direction, that is 0 minus of minus 1 is equal divided by 2 is equal to 0.5, that is h is equal to 1, k is equal to 0.5, and the integration points are given by Cartesian product of this psi 1 psi 2 eta 1 eta 2. So now we have weights and the corresponding locations of the integration points, so we can evaluate the integrand at those locations and multiply with corresponding weights and sum them up, we are going to get the estimate of the integral, which turns out to be 0.7778, whereas the exact solution is 0.8. So this is what I mentioned, since we under integrated, that is we used less number of integration points than required, the solution may not be accurate, there may be some error in the solution, and that is what is reflecting here. So now let us see how to use, here we use 2 points along x direction, 2 points along y direction. So now let us see how to evaluate integration over a rectangular area if we adopt 3 integration points along x direction, y direction. So we are having 3 points along x direction, that is psi 1 psi 2 psi 3, along y direction eta 1 eta 2 eta 3, and again similar to the previous case, half the dimension along x direction is denoted with h, half the dimension along y direction is denoted with k. So, once we have this, if we have the values of psi 1, psi 2, psi 3, eta 1, eta 2, eta 3, we can take Cartesian product of this and get the locations of all the integration points, and at each integration point weight along psi direction times weight along eta direction we need to multiply, and then we get the total weight. So, we first identify what are these psi 1, psi 2, psi 3 in terms of x coordinate or x1. So, psi 1 is x1 plus h minus root of 0.6 h, psi 2 is x1 plus h, psi 3 is x1 plus h plus root of 0.6 h. These can these values or these expressions can easily be verified once we know the locations of these integration points. And similarly, what are the weights at these locations? Weights at psi 1, weight at psi 1 is 5 over 9 times h, h is half the width or the dimension of the rectangular area along x direction, W2 is 8 over 9 times h, W3 is 5 over 9 times h. Similarly, eta 1 is y1 plus h minus root of 0.6 times k, eta 2 is y1 plus h, eta 3 is y1 plus k plus 0.6 times k, where k is half the dimension of the rectangular area along y direction. So, W1 is 5 over 9 times k, W2 is 8 over 9 times k, W3 is 5 over 9 times k. So, we have the locations psi 1, psi 2, psi 3, eta 1, eta 2, eta 3. So, we can evaluate integral f x y between the limits x1, x2, y1, y2 using this formula. So, we need to evaluate the function at each of the points psi 1 eta 1, psi 2 eta 2, psi 3 eta 3 and rest of the points, and multiply with the corresponding coefficients and weights, we get the approximate value of integral. So, we can apply this formula to estimate this integral again, which we already did with 2-point rule, 2-point Gauss-Legendre rule. So, the polynomial or the integrand is of order 3 along x direction, is of order 4 along y direction. So, to estimate this integral accurately, we already discussed that we require to use 2 points along, at least 2 points along x direction, at least 3 points along y direction. So, if you use more number of points along x direction, we are not going to get any more increase in the accuracy, but accuracy remains same. But along y direction, earlier we used 2 points, now we use 3 points and see whether we match the exact solution or not. So, using 3-point Gauss-Legendre rule in both directions and identifying h and k, h turns out to be 1, k turns out to be 0.5, and these are the integration point locations. And when we substitute these integration point locations and evaluate the integrand at these locations and multiply and substitute the corresponding values in the previous formula, we get this integral value, the estimate of this integral value to be 0.8, which matches very well with exact solution. So, since we actually use the required number of points along y direction. So, one more important thing that may be helpful for evaluation of multiple integrals is given here. If the transformation from x and y to use x and y space to u and v space is like this. X is equal to phi times phi as a function of u and v, and psi as a function of u and v, represents a continuous one to one mapping of closed region R of x y plane into the region R prime of u v plane. Then the function phi and psi have continuous first derivatives. So these are the requirements, and their determinant of Jacobian is given by this. Then determinant is positive everywhere. Then the integral fxy dx dy evaluated over region R can actually be transformed into the way that is shown on the right hand side of the equation, that is double integral r prime f as a function of phi and psi, which in turn are functions of u and v, multiplied by determinant of Jacobian du dv. So this kind of transformation we can use to transform the limits of integration from one set of values to another set of values. So this formula may be of help when we are evaluating multiple integrals. So that is why it is given here. So now let us look at how to apply these concepts for numerical integration over quadrilateral elements, and these formulas are called product integration formulas. Basically these are same as what we have already seen. Integral minus 1 to 1 minus 1 to 1, double integral minus 1 to 1 minus 1 to 1, f st dst is we need to select certain number of points along s direction, certain amount of points along t direction, and evaluate the function at these points, multiply with the corresponding weights, weight along s direction times weight along t direction. So s and t are the locations of integration points, m is the number of integration points along s direction, and n is number of integration points along t direction, and wi wj are the weights along s and t directions, and fst f si tj is function value at the integration point, and the total number of integration points are number of integration points along x direction times number of integration points along t direction, that is m times n. So now let us see what is meant by 1 by 1 integration, 2 by 2 integration, 3 by 3 integration. The figure below shows few commonly used integration formulas. 1 by 1 integration, 2 by 2 integration, 3 by 3 integration. There is if it is 1 by 1 integration, 1 point along s direction, 1 point along t direction. If it is 2 by 2 integration, 2 points along s direction, 2 points along t direction. If it is 3 by 3 integration, 3 points along s direction, 3 points along t direction, and the locations of Gauss points in each direction and the corresponding weights are same as those given in the table for one dimensional problems, which we already looked at. So they are repeated here for more number of integration points. So now let us look at the table. Here the locations and weights for integration points 1, 2, sorry 1 is not given, 2, 3, 4, 5 are given in this table, and one is the location is 0 and the integration, the weight at that point is 2. So n is equal to 1, the integration point location is 0 and weight is equal to 2. So it is not given in the table, but n is equal to 2, n is equal to 3, n is equal to 4 and 5, the locations and weights are given here, and similarly a continuation of this table is here with the rest of the points, n is equal to 6, 7, 8. And 9 and 10 number of integration points. So, looking at this table we can actually find the locations of integration points for 2-dimensional integration or 3-dimensional integration. And here if you see these tables, there is a gap after a certain number of significant digits. So, that space is nothing but depending on the accuracy that is required, we can go for more number of significant digits, otherwise we can chop off at that location where the space is there depending on the accuracy that is required. So, 1 by 1 integration, what is the location and the corresponding weight, they are given here. So, weight along s direction is same as weight along t direction is equal to 2, and location is s is equal to 2, t is equal to, sorry, s is equal to 0, t is equal to 0. So, we need to evaluate function at 0 0 and multiply with weight 4 . 2 by 2 integration, locations along s direction, locations along t directions, and weight along s direction, weight along t direction are given here. So, by taking Cartesian product of this s values s12 and t12, we get the locations of all the 4 integration points, and the weight at each integration point is weight along s direction times weight along t direction. Similarly, 3 by 3 integration, the locations of integration points along s direction and the locations of integration point along t direction is given, the corresponding weights are given. So, by taking Cartesian product we can get the coordinates of all integration points, and this we can apply to evaluate this integral using Gauss quadrature. And before we proceed, we see the integrand, the highest order along s direction is 7, highest order of this integrand along t direction is 6. So, 2n minus 1 is equal to 7 and n is equal to 4, and 2n minus 1 is equal to 6 results in n is equal to 3.5 or 4. So, to evaluate this integral accurately we require to use 4 points along s directions, 4 points along t direction, and if you use less number of points we get error. So, let us verify whether that is true or not. So, using 1 by 1 integration formula, so we need to, for 1 by 1 integration we need to evaluate function at s is equal to 0, t is equal to 0 and multiply with weight 4. Function evaluated at s is equal to 0, t is equal to 0 turns out to be 0 and the weight is 4. So, 4 times 0 is 0. So, the estimate of this integral using 1.1 formula is 0. And using 2 by 2 integration formula, the calculations are summarized in this table. Point 1 s and t locations and the corresponding function value at this point, first point, the corresponding s and t values, weight along s direction, weight along t direction, weight along s direction times weight along t direction times function value at point 1. Similarly, for point 2, point 3, point 4, all the details are provided in the table, and the estimate of the integral is the sum of all the values corresponding to 1, 2, 3, 4 points in the last column. If we sum up we get the integral estimate, which turns out to be 1.03703, And now let us try evaluating this integral using 3/3 formula. So the function is shown here. So we are trying to use 3 points along s direction, 3 points along t direction. So similar to the previous case, the calculations are summarized in a tabular format. There are total 9 integration points, corresponding s values, t values are given, corresponding weights are given. So the estimate of integral is nothing but sum of all the values corresponding to point 1 to 9 which appear in the last column, and if you sum up it turns out to be 3.36. So the estimate of this integral using 3/3 integration is 3.36, whereas the exact integral value is going to be 4. So to increase the accuracy here, we require to go for 4/4 integration. So now let us take another integral. And it is suggested to use, to evaluate this integral, it is suggested to use 2 points along s direction, 3 points along t direction. So let us check whether this leads to the exact solution or not. The highest order along s direction, the highest order of integrand along s direction is 2. So 2n minus 1 is equal to 2, so n is equal to 1.5, or we require to round it off to the highest side 2. Similarly, the order of integrand along t direction is 5, so 2 minus 1 is equal to 5, so n is equal to 3. So we require to use 2 integration points along s direction, 3 integration points along t direction to evaluate this integral accurately. So that is what is suggested. So the locations of these integration, 6 integration points along s and t directions are as shown in the figure, and this is the integrand, and the calculations are summarized. So we require to evaluate this function at each of these points and multiply with the corresponding weights. The corresponding weights are weight along s direction times weight along t direction. Again, as in the previous cases, sum of the value corresponding to all the 6 points 1 to 6 appearing in the last column, if we sum up we get the estimate of the integral, and so 2/3 integration results in 0.26666, and the exact solution also is going to be the same. So this is about applying Gauss-Legendre rules for evaluating integrals over rectangular area. So now let us look at integration for triangular elements, and this integration for rectangular elements, integration for triangular elements, these details are very important for finite element equation assembly or finite element equation evaluation. So integration over a triangular area is nothing but this kind of integral between the limits 0 to 1 minus t along s direction, between the limits 0 to 1 along t direction. We need to evaluate this integral fst, double integral fst between the limits 0 to minus 1 t, sorry 0 to 1 minus t and 0 to 1, and that can be estimated similar to what we did for rectangular elements. So we need to find the integration points first, and once we have the integration point location, evaluate the function at those integration point location, multiply with weight and sum up the contributions from all the integration points. So where Wi is the weight, Si, Tj are the coordinates of the integration points, m is the total number of points, and the table below shows the locations and the corresponding weights for the integration points and weights for integrating over a right angle triangle. So whatever may be the triangle, for integration purpose it is going to be mapped onto a right angle triangle where S goes from 0 to 1, T goes from 0 to 1. So number of integration points and the degree of accuracy associated with adopting this number of integration points, and the locations of integration points and corresponding weights are given in this table. So this helps us to evaluate this kind of integrals over a right angle triangle that is shown there, where the coordinates of all the key points are shown in the figure, where this n1 and n5 are nothing but quadratic or 6 node triangular element shape functions, and they are given by this one. N1 is equal to -1 plus s plus t times -1 plus 2s plus 2t, and n5 is given by 4 times s times t. So we need to substitute this n1 n5 values into the area integral n1 square n5 ds dt, and then we can decide the number of integration points, and then we can evaluate the function at those points and multiply with the corresponding weights to estimate this integral. So for a quadratic element, n1 is this, n5 is this, so the integral becomes this one. So integrand is nothing but -1 times, sorry, -1 plus s plus t times -1 plus 2s plus 2t whole square times 4st. So that is the integrand. So one point integration, the location of integration point is 1/3 and the weight is half. So one point integration results in 0.002744, 3 point integration results in this equation, and which simplifies to 0.002744. And 4 point integration results in 0.002657, and the exact solution or exact value of this integral is 0.001587. So we require to use more number of points, and the corresponding locations and weights can easily be found in any of the standard textbooks on numerical methods or finite element method. So this is basically the end of numerical integration, details of numerical integrations. This is the reason why we adopt Gaussian quadrature for evaluating integrals in finite elements, and for 3-dimensional case the extension to one more dimension is straightforward. So the locations and weights can easily be extended for 3 dimensions, following similar steps as we have done from 1 dimension to 2-dimensional case.